Okay, I think we're ready to go, everyone. So welcome to the second panel discussion in this opening session of this conference, Net Zero and Beyond, Pathways to Decarbonization. Thank you, everyone, for joining us today. This is a challenge that I feel is sometimes overlooked, but one that is growing certainly in certain areas. Development and rapid deployment of low carbon energy technologies and infrastructure are considered the primary pathway towards net zero reduction and net zero targets, emission reduction and net zero targets. However, such a transition will undoubtedly require a substantial increase in demand for materials, including critical metals. The extraction, processing, and manufacture of these materials does have ecological and societal externalities, which could compromise other sustainable development goals and possibly a number of geopolitical consequences. This panel will consider the scale of the energy materials dilemma and discuss some potential solutions and research and development pathways. My name is Lewis Collins. I'm the editor-in-chief of One Earth, Cell Press's flagship sustainability journal. And I'm delighted to be joined today by this fantastic panel. We have Professor Elsa Olivetti, the Esther and Harold E. Edgerton Career Development Professor in the Department of Materials Science and Engineering at the Massachusetts Institute of Technology. Elsa is also the co-director of the MIT Climate and Sustainability Consortium. We are joined by Damien Giurco, the Deputy Director at the Institute for Sustainable Futures at the University of Technology, Sydney. Professor Doug MacFarlane, Sir John Monash Distinguished Professor of Chemistry at Monash University's School of Chemistry. Doug is also Energy Theme Leader of the Australian Centre of Excellence in Electromaterial Science. Yi Shui, Director of the Precourt Institute for Energy Department of Material Science and Engineering at Stanford University. And last but not least, Alissa Kendall, Professor of Civil and Environmental Engineering and Chair of the Energy Graduate Group at the University of California, Davis. We'll shortly jump into a keynote from Elsa. Following this, each of the panelists will give an overview of their own work before we jump into, I'm sure, will be a very interesting discussion. If any audience members, any viewers would like to pose your own questions, please feel free to do so via the Q&A interface. If we have time, we'll certainly put these to the panel. If you do want to ask a question, please try to do so within the first 1 hour to 90 minutes, just so that we have time to share them and ask. Well, that's plenty from me. If everyone, apart from Elsa, could turn off their cameras and mute themselves, that would be great. And without further delay, Elsa, over to you. Thank you very much.
Excellent. Thank you so much, Lewis. I'm grateful. We'll just see if we can get things loaded as we should. And I trust folks will tell me if they're not loaded appropriately. So I'm grateful for the introduction and the opportunity to share with you all some thoughts, sort of high-level context setting for our discussion, which I'm eager to get to, particularly around this challenge of the material low-carbon energy dilemma. And Lewis already alluded to this a bit, but the ultimate dilemma we face here is that our low-carbon future is definitionally mineral intensive, right? So many of the technologies we consider necessary for a transition to low-carbon energy production really rely on key materials. And any gaps in the availability of those materials are going to get in the way of that transition. And the low carbon future we know to be mineral intensive because clean energy technologies tend to need more materials than fossil fuel based electricity generation technologies. And so ambition on climate change, if we are actually to get as serious as we need to, as outlined by the Paris Agreement, requires installing more technologies and therefore leads to a larger materials footprint. And this creates a set of tensions and trade-offs that really requires a systems-based, scalable, and cross-disciplinary set of solutions. And I have this assertion that we're going to need to embrace the complexity that is going to need to be solved, and this necessitates collaboration. So that's the punchline of what I'm going to say to you all today is we need to be able to figure out how to manage this complexity. So what I'm hoping to do in the next bit is to frame some of these issues, some of these tensions that we can really talk about and get into detail in the session itself. So to begin with, we know that electrification in of itself, as alluded in the previous session, really requires both generation of low carbon electricity, as well as facilitating its use in energy heavy sectors. I'm going to get into details on the metals themselves, but just to kind of frame in terms of the technologies, which is the subject of the previous session. On the supply side, when we're thinking about supply of energy, obviously there's renewable electricity generation in the form of the sets of renewable technologies we would consider, but also distribution and expansion of the grid that we need to meet that decarbonized electricity demand, and then supply in terms of storage as well. On the demand side, we have to think about transportation, electrification of industrial and residential heat, and industrial processes, some of which I've listed here. And this is a little bit of a foreshadowing to later sessions in this conference. And we can begin to think about how we might roadmap some of these various supply and demand technologies. So the 2020s are about removing emissions from the grid and running as much as possible in transportation and heating and electricity, and upgrading and expanding that grid. And then while that's happening, put research into investments in storage that would really come into fruition in the 2030s. So energy storage from the grid, carbon capture, and that we fully electrified automotive transportation. And then in the 2040s, really move to electrify and manage decarbonized tough sectors. So that's a bit of a sense of the temporal horizon for that materials use as it manifests in the various supplying of energy and electricity and demand for particular services that are decarbonized. So now with that framing, let's dig into what technologies are relevant, what materials and minerals are relevant, and how each of those manifest in demand and some of those complexities that I went to. So here we have just a radial button summary of renewable energy technologies and some of the distribution network requirements by material element, where they're colored by the degree of criticality or the degree of supply challenge around that. And we're going to get into that in much more detail as we go through. So we see red is high, orange is moderate, and blue is low. But you also see the distribution of these various minerals throughout the technologies that are relevant. And so why do I put that particular framing that are, as we transition, that has this low carbon material dilemma? What is that manifested in? So I'll show you a couple of different ways of looking at that. So one is just comparing across transportation and then power generation. If we compare sort of incumbent technologies to materials, to more advanced low carbon technologies, what I'm plotting here from the IEA in 2020 is just how the different elemental uses in that comparison. So comparing a conventional car, which materials intensity is dominated by copper and manganese, to an electric car that has not only much more diverse set of mineral palette, but also that those are much more intensive materials uses. And similarly, when we think about renewable energy and power generation, the incumbent technologies in coal and natural gas as compared to the multitude of renewable energy technologies. And again, we see much more materials intensive. So this is per kilowatt hour, per megawatt in terms of each of these technologies. And so that's one framing of the materials intensity requirements in a low carbon transition. But we also see not only we'll obviously have larger scale demand for each of these individual technologies. And we can see how in this also from the IEA, that where we're looking at now the share of clean energy technologies in total demand for selected minerals from 2000 to 2020, and then projected out to 2040, in the two different scenarios, and the stated policy scenarios and sustainable development scenarios, again, as purported by the IEA. So we see the significant increase, not only in terms of quantity, but also in terms of total share. So the diversity of palette, increase in market share. And then the other thing that's really significant in this is the relative demand growth, which is particularly high for battery-related minerals. And the rapid deployment of these technologies as part of the energy transition implies a significant increase in that growth rate. And so here I'm showing by metal demand growth by 2040. We see a significant range there, which is a point I'll get into in the next slide. But not only meeting this significant demand, but also meeting it at the rate at which it needs to is another important point that I want to bring out in the framing conversation here to try to set the stage for our further conversation. So this is just a couple of different framings of how to think about the energy sector really leading as a consumer of minerals as energy transitions accelerate. There's a lot of uncertainty, obviously, in that. And this is because new technologies for energy conversion and storage, are going to take roughly 5 to 15 years to manifest, which means we have significant long-term uncertain demand. And so this ARENA roadmap from the International Renewable Energy Agency is just showing a series of different scenarios and what that means in terms of growth of technology. And the point of showing this here is just, as I said, there's a lot of uncertainty in what that range is going to be and what that materials requirement is going to be, which means it's difficult to plan, difficult to make sense of all that. And so what you see in this plot by element or by mineral is the IEA scenarios in these sort of gray and light blue color, and then the ARENA roadmap is a much more significant map. Total demand requirement. So just again, to try to emphasize that there's a range in what's required as well. And we can think about this by element again, where I'm showing the projected annual mineral demand in percent increase relative to 2018, where the top of this graph is 500% for graphite, and then total quantity in millions of tons here on the bottom. And so production of things like graphite, lithium, and cobalt are needed to be significantly ramped up by more than 450% by 2050 relative to 2018 levels. Whereas the demand for some base minerals like aluminum and copper, so here's copper here and aluminum here, maybe that's not a significant percentage increase. The total absolute production figures, as shown on the right here, are quite significant. And these projections that are shown here, there are different ways of framing these. So this, for example, doesn't include the storage requirements necessary. These estimates here don't require infrastructure. So we can talk, we're going to have an extensive conversation about what those specific numbers are, but they're uncertain. And so trying to figure out how to meet that demand, given that it is one framing of the challenge. So significant diversity in palette and significant uncertainty associated with what that demand will be, which makes it challenging to plan. Another dimension of this, as we all know well, is that there's going to be a lot of shifts in geographic concentration from incumbent technologies, so shown for extraction on the left and processing on the right for fossil fuels, oil, natural gas, oil refining, and LNG export. Here we're showing the share of the top 3 producing countries in production of selected minerals and fossil fuels. So we see the country dominance for fossil fuels versus the sets of materials associated with renewable energy technologies. And it's a pretty different geography. The colors are different from what's above, but not only that, it's much more concentrated. And this is a story we all know well. For example, the concentration of cobalt extraction in the Democratic Republic of Congo and subsequent emphasis and concentration in the refining in China. So significant shifts in the landscape for these supply chains, which adds other sorts of pressures onto the system, but also that those become particularly concentrated. So we're more vulnerable to particular supply chain disruptions as they emerge. And I'll talk about that in a little more detail as we go forward. So as I said, the scale up for this new technologies is measured in decades. So that's one temporal aspect in terms of the uncertainty of what's going to be demanded. But in addition to that time horizon, another temporal factor is the time to prospect, research, plan, fund, get permits, and deploy new mining and processing technologies. So here's just a couple of different ways of framing that element of another temporal horizon that we have to track and plan around. And this is shown in two ways. One, just kind of breaking down the mining project. So when we're considering new primary supply and the ways to meet that primary supply, we have to think about discovery, resource estimation, the size and the grade of a particular deposit, and that might be one particular off-ramp, set of pre-feasibility studies and feasibility studies along multiple dimensions. And so each of those signposts or go, no go kind of points shown on the left manifest in a significant time horizon. The global average lead times based on 35 top mining projects that are shown up here in this plot on the right from 2010 to 2019 shows this range of up above 15 years to until we would reach construction and production. And then this is broken down, the lead time for selected minerals that we see in lithium, much shorter, in lithium in Australia, shorter time horizon up through copper and different nickel deposits, types of nickel deposit, which we'll talk about as well. So these are just further complexities and tensions that we have to think about. Overall need more of these minerals to meet demand, but we have to think about what the uncertainty of that demand is and how are we going to have supply meet that. Which transitions to the next framing set of comments that I want to make. That's about supply and about materials availability. So the question we often ask is, are we going to run out of these minerals? Is there enough of any of these metals and minerals to meet supply, to meet demand? And I assert that yes, it's not a matter of whether or not there is physical constraint in large part when it comes to meeting this demand. It has to do again with our ability to respond quickly, and how that manifests is in terms of price. So there may be practical limits on energy technology scaling based on volatility that we see as supply chains are more volatile because of the ways in which they have to ramp up demand in particular. And I'm going to dig into this point around materials availability in a little bit more detail based on some work that we've done in my group, looking at some of these materials availability issues. So I will assert that it's not about running out, it's about managing this risk and these uncertainties that I've mentioned as I've gone through, and the influence of price on that. And so whether a material is critical or is not, whether or not there's enough, but whether or not risk based on these factors is deemed too high, and therefore, this concern leads to price impact. So what we see in the plot on the left is work done at MIT by Professor Yatming Cheng and Bill Green that found that materials costs can begin to set practical lower bounds on battery price. And so what this is a two-stage learning curve model that projects actual active materials cost shown in that green line there over time in dollars per kilowatt hour using batteries as a technology example. And we see this learning curve that's associated with the manufacturing of this battery pack that is coming down, and it starts to meet this floor that's associated with the materials costs and then subsequently the minerals cost that's shown below that. And so the takeaway here is that materials costs may set this floor. So understanding these materials risks, therefore criticality risks that can influence this cost is critical. So saying this another way, criticality is not scarcity. It's a function of the market imperfections that are inherent to a specific material, the set of functionality constraints, the degree of substitutability, the various feasibility of alternatives, and the particular importance of a technology. And I'll get into this in a little bit more detail as we go down, but the nature of the extraction, whether or not a mine is being set up to extract the particular mineral that's relevant for that energy technology. And those are the sorts of factors that are at play here. There are many different ways of framing criticality. That's done by company often or by government, and where there's different frameworks for how those criticality is evaluated. Again, not about running out, But here's a framework by Tom Gradle, which is, balancing the sort of sets of supply risk, sets of vulnerability to supply restriction, and environmental implications of that. And so there's many different sorts of metrics that we might start to tease out to inform whether or not there are criticality issues in a screening, et cetera. But it's not that the minerals are rare or expensive, but instead that there's going to be subsequent, risk associated with any of these metrics that are listed on the screen. So these are the sorts of things we need to think about when we think about meeting the supply for an increased demand in these electrification technologies. As I said, I just wanted to dig into this a little bit more detail, just to give some examples, particularly as it relates to energy technologies, primarily materials associated with batteries. So what I'm going to show on this plot here on the x-axis is a fraction in top country, where a material is mined, getting to that geographic concentration I talked about earlier. And then on the y-axis, I'm showing reserves, so the economically extractable amount of material divided by primary mine production. Sometimes that's called the static depletion index, and I'm going to show it over time, first for a set of more commodity minerals, although so what you see in color here is for manganese in green, nickel in gray, zinc in blue, and lead in a lighter shade of gray. But I'm showing this depletion versus fraction in top country over time. And we see on this plot is just kind of a mess of dots, indicating the sort of maturity of these markets. And over time, we're basically finding as much as we need as a function of things being economically extractable. If we compare that, the sort of change over time in concentration and so-called static depletion index to more energy sensitive minerals such as lithium, vanadium is relevant in flow batteries, and cobalt. Again, I'm showing those same points over time from 2005 to 2020. We see much more movement, and in particular, I've tricked you with these axes here now, go much broader. So if it was 0 to 80 on the left here, now I'm 0 to 500 in terms of my static depletion index, and I'm showing a much broader rate in the fraction in top country as well. So my point here is not necessarily exactly where these dots are, but is more about the fact that they're moving. A lot of volatility associated with stabilizing the supply chains for those, which means that we have a lot of potential for price, significant price excursion that we need to plan for. And in particular, as folks know, there's lots of discussion around cobalt. So cobalt is particularly concerning on this plot because it's going down, meaning we're not necessarily finding economically extractable reserves at the same rate we want them, and that it's becoming more concentrated. And this is a story that's played out several times in the popular press. And the degree of concentration of cobalt in particular, as I said already, is not only relevant in terms of its extraction from the Democratic Republic of Congo, but also that refining is dominated in China. So it's got supply concentration throughout the supply chain, or geographic concentration throughout the supply chain, excuse me. And here's that shown just graphically, comparing the supply chain in US dollars of export in red and import in green, geographically for cobalt on the left and lithium on the right. And just even without digging into any of the details, we see this juxtaposition of these flows indicating the relative concentration of these. So these are other kinds of metrics that we think about when we think about screening for materials availability. Another point that's particularly critical for cobalt and other energy relevant metals is the byproduct nature of cobalt extraction. And what I mean by byproduct here is that the byproducts are metals that are mined and produced as a consequence of extracting another material. So that means that they're very contingent on the dynamics of the so-called carrier materials, as opposed to the mine material itself. Versus something that's a co-product, which means that we derive revenue similarly across the mine products. So the flowers that I'm showing on the left there are showing that cobalt is mined primarily as a byproduct of copper, where copper is the center of the bottom flower there, and nickel in the purple flower there. And so that just means that a mine is not necessarily being set up for extraction of copper and nickel, for cobalt, but rather of copper and nickel. And the relatively complex chart on the right there is just indicating that just simply saying that something is mined as a byproduct is not necessarily sufficient, right? So this gets a little bit to the complexity point that I was making at the beginning. So in this plot, we're showing byproduct fraction on the x-axis and value ratio on the y-axis, showing that whether or not, that whether or not something is going to have a materials risk associated with its supply as a function of being a byproduct is going to vary by what the relative ratio, the relative revenue of these are, and the relative extraction fraction that is mined as a byproduct. So the bottom right-hand corner of this plot, where energy metals are highlighted in green and their byproduct carrier pairs, are the ones of particular concern. And you can see there indium, cadmium, selenium, may be relevant in solar technologies, but then we see the cobalt and nickel there as well. So just other sorts of metrics that are of interest in trying to assess supply concentration. The other point that I made at the beginning there was around growth and demand growth in particular. And so again, whether or not we have enough is a function of time, and not having enough at the right time, essentially. And so here we're showing, again, for example, minerals that are relevant in energy technologies, the historic compound annual growth rate, juxtaposed with a compound annual growth rate requiring a particular deployment level. So here I'm showing 100 terawatts through 2050. And we see that for the case of lithium, the compound annual growth rate of 100 terawatt hours, which is an estimate really of grid storage only needed by 2050. And, if we think about electric vehicles on top of that, that could be, double that we're on the edge of the historic compound annual growth rate. Versus, something like cobalt, or even more concerning nickel, we're above that historic compound annual growth rate, meaning that the supply chains and mining projects that I just told you take 5 to 15 years need to accelerate quickly in order to meet these needs. Another further wrinkle on nickel is that, as folks might know, there are two classes of nickel. Class 1 nickel, that's a high purity nickel, which is relevant to battery grade nickel, versus a class 2 nickel that's much more relevant for nickel as it's used in steels. And the majority, upwards of about 70% of nickel that's currently extracted is not relevant for battery grade technologies, meaning that some of the potential expanded projects are not necessarily relevant in terms of the growth rate on this. So many different layers of complexity here in terms of our ability to grow quickly, in terms of our capacity, and for the right type of mineral to be extracted. And so just wanted to kind of summarize a little bit some of the supply challenges before we talk about some of the environmental impacts. And not all of these did I get into detail about, but here I'm just showing some high-level challenges associated with supply of copper, nickel, and lithium. And I've just put the process flow diagrams there, just sort of to remind us that not only do we have to think about the resources extracted, but also the downstream processing. And do we also have the capacity for that as well? And so copper, we have challenges in terms of, the ability to substitute these, but also to substitute copper based on its properties, but also the declining ore grade that I'll talk about a little bit in a minute. And then water stress concerns, which I'll also talk about. And nickel is, as I just mentioned, the challenges of nickel as currently extracted is not necessarily meeting our needs in terms of its use in battery grade products. And lithium as well, there's potential downstream challenges in terms of the chemical production. Lithium is used in batteries as a hydroxide or a carbonate, and so the precursors to lithium in batteries is as a carbonate or hydroxide, and so some of the materials challenges associated with meeting that processing need. So the point here is that these supply challenges are going to vary by mineral. It's not a monolith, and so the solutions that we consider need to be taking those into account. And then the other little point I'll make here, when we think about primary supply, and this is, we'll get into in discussion as well, or excuse me, when we think about meeting demand, mostly what I've talked about here is meeting that through primary supply. And so the natural question there is about recycling and how do we think about use of secondary material instead to meet that demand? And I like to juxtapose that the challenge when we think about recycling meeting this demand in the immediate is to just think about these two plots side by side. So on the left, I've got light and heavy duty electric vehicles as placed on the market over time, forecasting by region and by type of vehicle. The details are not so important. And on the right is electric vehicles reaching end of life on the global market. But I've tricked you here. I've got the x-axis off by an order of magnitude. So if I actually juxtapose these plots and put them correctly, side by side, we know that at least in the immediate time horizon until about 2040, 2050, the supply coming back from end of life is not going to be as relevant in terms of meeting that demand. So when we think about circularity and circular economy, we have to make sure we're thinking about, what is the ability for that secondary supply to meet demand in the short run, and so that points us to needing to continue to think about, how do we impact the overall emissions associated with the set of materials that I've just, made the case that we're going to be extracting, from primary. It's going to need to happen to a significant amount in order to meet these sorts of demands. And here I like to frame this in terms of, what are our levers for impact, as shown in I, that we can think about the amount of population that we have, the wealth of that population. But if we think about sort of, as often the case in several of the IPCC conversations, we want to have significant quality of life, then our levers end up being thinking about both technology and behavior on the demand side, which we'll come to in the panel and discussions, thinking of and juxtaposing that with levers of opportunity we have in the carbon intensity themselves and the emissions intensity beyond carbon of the energy supply and the materials of which are the focus in what I'm talking about here. And so just want to leave us with a couple of thoughts here in terms of I've made the case that we're going to need more materials. In addition to that, several of these energy transition materials are going to involve higher GHG emissions intensities associated with their extraction. And so I'm just showing some examples of that here, where on the top plot there, we're seeing tons of CO2 equivalent per ton of metal content for a variety of different metals broken down by their processing and mining impact. But some of the sorts of technologies that I just flashed up in those process flows are going to have higher emissions because of the process requirements or because of learning. So in the case of nickel, for example, the majority of the way it's extracted now is around 5 to 10 kilograms of CO2 equivalent per kilogram of nickel. And some of, moving to some of those process pathways that give us battery grade technology, as I mentioned before, are going to increase the emissions associated with that. And similarly, think about lithium technologies for moving from more brine or salt-based extraction to more spodumene to other kinds of precursors. That's also going to mean we have additional emissions associated with this extraction. So if you couple that, this sort of increased intensity by process, we also have to think about ore grade declining, which has been particularly talked about in the case of copper. Here, just showing an example of ore grade decline in Chile over time. And so, so then again, we have to think about changes in process emissions, changes in ore grade linked with this quantity. So lots of reasons to be concerned and to make sure we're pursuing all the strategies that we can in terms of realizing this. And of course, it's not just about carbon. There's also significant environmental risks that go beyond emissions in terms of land use, water stress and waste. So here, again, plots from the IEA that are showing overlays of extremely high water stress areas with where copper and lithium mines are. And then the bar plot there is showing where we have high water stress as measured by water withdrawals compared with the nature of the water in that particular areas, the total available surface and groundwater supplies, for example. It's not just that. There's challenges in waste, mined output going down as a function of ore quality, as I said, leads to higher tailings, et cetera, as we move forward. So I presented, several different framings in terms of how we think about the amount of materials and the challenges and the intensity of that. And then, we start to think about recycling, which we'll come to, but I've made this case that it's difficult to think about recycling's ability to immediately meet that demand. And it's also, given the delays associated with recycling having any kind of immediate impact on supply, there's an information delay there from, as we signal in the market of various recycling mandates and recycling contracts. Well, where does that actually manifest in the mine level is a challenge as we go forward. And so let me bring you to my final thoughts here. Excuse me, there they are. So just some summary thoughts here. So materials demand that is going to need to grow to meet these decarbonization needs, but the challenges across materials are not monolithic, and hopefully I've made that case for you here. Whether or not something is available or not, the physical scarcity is not necessarily a major concern, but rather these sort of temporal and contextual issues, technology evolution, mining operation, recycling becoming viable really as demand declines, so that we're able to mine urban contexts. Now I've alluded to or briefly touched on the significant environmental impacts that are going to be associated with the continued materials extraction. And I think as we'll get into in discussion, materials efficiency and things like recycling and dematerialization are going to play a role, but let's be specific about what that role is going to be and the time horizon over which that can manifest. So thank you so much. I hope some of these thoughts were useful in framing. And now we turn to the rest of the panel.
Many thanks, Elsa, for a really interesting talk with lots of challenges. I think we can agree we have there, and hopefully together we can identify some of the solutions. Okay, moving swiftly on, fantastic time management. If we could now jump into the individual panelists to give an overview of their work. Damien, if we could kick off with you, that would be great. Thank you.
Thank you, Lewis and Elsa, for your presentation, which really nicely laid out the challenge and how we can approach responding. And I'm really looking forward to further discussion with the co-panelists today. It's great to be here with you, and as I begin, I'd like to acknowledge the Gadigal people of the Eora Nation, upon whose ancestral lands the University of Technology Sydney stands, and pay respects to elders past and present, and acknowledging elders as traditional custodians of knowledge for country across thousands of generations. In addition to a great sense of humour, one of the things that I admire about Aboriginal culture in Australia is the wisdom that comes through recognising the interconnectedness of resources in nature, and that interdependence between healthy land and water on country, and indeed in our natural world, that is absolutely necessary to sustain you and I and other life for generations to come. And as Elsa laid out, we need to be better at thinking and working in complex systems. I'd say not only technical systems, but ecosystems and social systems. And that's really a take-home message from me today, is as we examine this materials low carbon energy dilemma, is to focus on sharing knowledge and practices that can really help bring that to fruition. And indeed, this collaborative systems approach is one that underpins our research at the Institute for Sustainable Futures, where for the past 25 years, we've been working to create change towards sustainable futures across the range of areas that you can see on the slide. And an important part of the discussion today is really where will our metals come from that are going to be needed to underpin this rising demand for our future energy systems. So we can see here plotted the total material requirement, how much material are we going to need to move, looking out from 2015 to 2050 to the future electricity sector. And that small blue wedge over time is referring specifically to the metals. So that is blown up here. You can see rising iron and copper and nickel and so on, but quite a decline in the mining of fossil fuels, coal here in particular. For the transport sector, and apologies if you can hear jet aircraft roaring in the background, I'm waiting for some nice electric planes to be landing at the airport nearby in the not too distant future. But you can see such, firstly noting the different scale here, but such an uptick in the metal requirements, and a huge contribution of that comes from electric vehicles. Now, here, this paper has put together some data on not only where the materials are to be mined, but also the governance regimes in place in those countries. And I think why it's also important for us to reflect on this is that social license and governance and environmental conditions and impacts can feed into the not only how the benefits are shared from this mining, but also the delays in getting mining approvals up and going. And I'd like to say some important work that we're doing at the Institute, particularly led by a colleague, Stephen Northey, is to start to bring a mine-by-mine approach to the mapping of supply side, metal supply and mining and exploration. It's important that knowing primary mineral supply, as Elsa said, is going to be such a large part of the future equation for meeting demand, that we think about what it means to supply that responsibly. So some work we're undertaking with the Future Battery Industries Cooperative Research Centre is looking at life cycle assessment of Australian battery minerals. So in particular, lithium, we're a large producer, nickel, cobalt, vanadium, graphite, and to better understand the contemporary footprint for Australian minerals and how does that change, for example, as we increasingly connect to renewable energy to grind and process that. And what role can certification of responsible supply through things like Initiative for Responsible Mining Assurance or SEER and other approaches do to help build good credentials that end users are seeking as they're looking to put these battery minerals, for example, into electric vehicles. Just some of the components there we're working on in the project: understanding certification, better data for life cycle modelling, benchmarking, and exploring a range of future scenarios with different research and industry partners. I'd like to briefly call out a companion project led by Curtin University that's going into detail on trusted supply chains. So the two dimensions there are a geochemical fingerprinting, in effect, to verify that the ore has indeed come from Australia, where end users or automotive companies and so on putting lithium into their vehicles are interested in that. And secondly, exploring a blockchain platform to give that information to who needs it securely along the supply chain, and whether that's for provenance or indeed for the environmental and social footprint that is information we're developing through our life cycle assessment. This is to flag that over the horizon, whilst today and in the next decade, the story is going to have a heavy emphasis on primary supply for the needs of the renewable energy transition. Looking ahead, we are going to need to think differently about our materials stewardship. And so these graphics here for copper and nickel show total copper demand with a baseline scenario or a 2-degree scenario consistent, and noting the need too for a lighter colour with a higher proportion of that coming from recycled content. And so part of the planning now to have this available is also thinking about our product stewardship, whether that is for batteries or for solar cells and wind and other. And we've worked to recently establish with some Australian government funding Centre of Excellence for product stewardship that is sharing knowledge about how to do this well. So I'll finish with some closing thoughts that we might pick up further in the discussion together. But as we're thinking of this dilemma and how to solve it, we should pay attention to good design, energy and resource efficiency where we can, because it's so cheap and easy, even if it doesn't solve the whole story. That we need better data on what we have, primary and secondary sources, stocks, below and above ground, understanding with more sophistication how they could come to be utilised in a time sequence, their changing impacts with differing technologies and energy mixes, and how do we then build in and start to scale the responsible sourcing of battery minerals for this transition, and keeping at heart that systems view. And whilst trying to go fast, also thinking about the communities and the social license affected at mine sites and surrounds, and how we twin that local and global governance and be explicit about the trade-offs and don't go just for this panacea of broader integration. And where we can, scale up those circles. I'll finish there. Thank you.
Thank you for that, Damien. That was really interesting. We have some feedback on the call. I don't know if the person can hear me, but if they mute themselves, that would be great. Moving on, Alissa, could you, if you're still with us, Alissa, yeah, could you take it on from here?
Yeah, thanks so much, Lewis. I just want to say it's a pleasure to be part of this panel and hear the excellent talks that Elsa and Damien have already given. My name's Alissa Kendall again, and I hail from UC Davis. And I want to start by
UC
honoring
加州大学戴维斯分校.
All right, I'll keep talking.
It's okay, I'll try and resolve this.
Yeah, I'd like to honor the students and
首先呢，就是我要感谢一下我的整个团。
I think it's one of the
translators. Alissa, I think she's translating what you just said. Maybe you need to go to interpretation and select the channel. Select English, that's my guess. Then when she translates into Chinese, you will not hear her.
All right.
I'm not sure. Maybe Alissa, carry on and try to pay less attention to the translation.
Yes, indeed. Oh, okay, will do. All right, so I'd like to acknowledge the team that contributes a lot of the research that you'll see here, who are come from our industrial ecology program at UC Davis. And I'm going to focus in a bit on electric vehicles and electric vehicle batteries. We've already heard about their role in decarbonizing or a decarbonized future. And of course, the big challenge there is the lithium-ion batteries that they rely on. And the rapid increase in demand is essentially creating new global supply chains. Not that we didn't demand lithium before, but the scale of demand is such a magnitude in increase that we're looking to develop new resources and really create new supply chains. But of course, it's not just about making these batteries, it's about what happens to them when they're retired. And so you'll see here that, once we use our batteries, we have a lot of options to what might happen to them, including reuse, refurbishment, and recycling, as well as disposal or final disposition. And that can have a significant effect on how and whether secondary materials will play a role in how we make batteries in the future. But I want to start by some of the positives. So there are great environmental benefits to recycling lithium-ion batteries. Recycling impacts across many categories, including CO2 or greenhouse gas emissions, but also other emissions like air quality pollutants, you'll see there on the right. What I'm showing you here is essentially the net emissions shown in the black dots, assuming that secondary materials displace primary or virgin materials in batteries. So you can see a great reduction in emissions. And up here are just different recycling technologies that might be used in the future. Other questions arise around this. So recycling can really help reduce the impacts of this important technology and the metals used in them. But of course, we don't really have the recycling infrastructure right now to handle those batteries. And in some respects, that's okay. We don't yet have a flood of batteries being retired from vehicles, but we can look to the future and see that they're very large. What I'm showing you here on the left shows you the relative market share of manufacturing demand and recycling. And I'm here in the US, and you can see that we have essentially the most dramatic gap between recycling infrastructure and demand for lithium-ion batteries. And that's going to be a real problem as we see electric vehicles retire. I do want to point out that we do have a lot of growth on the horizon here for recycling. Essentially, in public announcements alone, we'll see a 350% increase in recycling capacity for lithium-ion batteries here in North America. But we'll still have a deficit relative to what might be needed in the future. And one thing we should think about is when we can see a problem out there on the horizon, policy can play a really important role in making sure that we have that infrastructure in place when we need it. But I'm talking in the future tense because even under the best and most optimistic assumptions for what recycling might do to supply secondary materials, we really aren't going to meet the demand for metals using secondary materials. So what I'm showing you here is a projection of lithium-ion battery demand in the future, retired capacity coming out in different global regions, and on a global scale, the potential circularity for different metals, assuming a closed loop system, assuming that lithium-ion traction batteries are going to be, the metals there will be recycled back into those batteries, which is not necessarily what would happen. But I say this to point out that even under the best conditions, out to 2040, for example, a best case scenario would be between 50 and 60% of material demand met by secondary materials. So if we can't actually meet future demand with secondary materials, we probably need to figure out how to produce primary materials better. And so what I'm talking about, what I'm showing you here is some photographs of California's so-called Lithium Valley. This Lithium Valley doesn't exist yet, meaning that we're not producing lithium there. But there's a region called the Salton Sea region in Southern California. You can see from the pictures it's a very arid and in some places quite desolate place. Currently, there is geothermal electricity generation occurring, and you'll see that in the figure, the photograph there. These geothermal, the geothermal brines that are currently brought up for electricity generation are quite lithium rich. And there's a potential to essentially couple this renewable electricity generation with direct lithium extraction. Direct lithium extraction uses a membrane technology instead of evaporative processes like most brines for producing lithium, and are considered more environmentally sound method for producing lithium, although we haven't really done the detailed life cycle assessments that will be needed to really verify that in the future. So I'm presenting this as sort of a positive story, an idea that we might have this sort of great coupling of renewable energy and lithium production and a production process that is less impactful to what we currently see out there in the world. But it would occur in the backdrop here in a region which has terrible air quality, high unemployment, relatively high poverty rates, and communities where in many communities where residents don't speak English. The English language issue is really one of whether or not they can participate actively in the public processes that would give them voice to talk about whether or not they want this kind of development happening in their community. But this could be a test case for really seeing whether under the best conditions, can we develop lithium minerals, and in this case, it's lithium, but it could be other minerals as well, in a way that prioritizes or essentially is shaped by socio-environmental priorities. And so can we develop mineral resources in a way that honors the principles of energy and environmental justice? And right now, the state of California has developed a commission that includes community members, the industry and state agencies to try and drive that process, try to start that process off. Elsa did a great job of showing you kind of the issue of lead times for minerals development. And one challenge is this will clearly slow down that first phase. If you have to get community buy-in, you have to make sure that communities are benefiting and not harmed by these developments like this. That might slow down development in the beginning. But on the other hand, in the long run, we might be able to do this kind of development right, and potentially speed up the process later on. I'm familiar with the US process, and especially in California, permitting alone can take many, many years, but doing it right can speed that process up, especially if community members are included for the beginning. So I don't have any research complete here yet, but our early research shows that right now the priorities among community members and the commission are a little bit at odds, although they agree on a lot of issues. One key difference is water. And I think, again, Elsa did an excellent job of showing up the tension between metals production and water scarcity. And as you can see from these pictures, this is a very water scarce region. So with that, I will pass on the virtual microphone to our next panelist.
Many thanks, Alissa. Doug, over to you.
Thank you. Let me just share a screen here. Here we go. Okay, so I'm Doug MacFarlane from Monash University, and as Damien has already introduced the significance, if you like, and especially to today's context of our Aboriginal nations. And in the case of Monash, I wish to acknowledge the people of the Kulin nations on whose land Monash University operates, and I pay my respects to their elders, past, present, and emerging. And as Damien said, this is one of the oldest cultures on the planet, and who have plenty to teach us all about maintaining their environment in the best possible state. So our interest as a group, research group, is comes under this banner of this gorgeous concept called liquefied sunshine. And of course, it's not limited to sunshine. This could be wind energy as well. And recognizing Australia's massive capacity to generate renewables, the big question emerges, if you look at our little graphic on the right there, how do we send this energy out of Australia, especially from the far northwest, to the populous markets of the north, to the north of us? So the question in our research is all about how do we transport renewable energy? How do we export it? And as a bunch of electrochemists, our interest is in electrolysis as a key technology in this respect. And of course, that brings up all of the materials issues around the materials that are in an electrolysis cell. So I won't go into that in depth right now. I think that will come out in discussion in a moment. Although some of the key elements have already been mentioned in some of the things that have been said already this afternoon. But in our interest broadly, we are interested in electrolysis processes that produce both hydrogen. So that's both a very traditional approach to effectively storing that electrical energy, But of course, there is much yet to be done to further optimize and shift the emphasis in that process away from the very precious materials that are often used. Once again, unfortunately, in terms of the periodic table, the platinum is the gold standard. Platinum standard material for reducing water, and if you want to know what is the very, very best at water oxidation, it's very hard to go past iridium. So iridium oxide, two very, very, very precious metals, of course. So huge amounts of research being done on, including from our group, on getting away from precious metals and into the realms of more common or garden materials. And then coming along more recently is the concept of similar processes to produce ammonia. And so I'm going to in the end, finish off in a moment talking about the role of ammonia in this big global picture. But just to put this in a more immediate energy storage and transportation context, in my next slide here, the approaches that we identified, and there's a paper that you can read from a few years ago that gets into this in a bit more detail. The approach to transporting large quantities of green hydrogen, of course, borrows immediately from the current global trade in liquefied natural gas. Problem is that hydrogen is even harder to liquefy and transport, and all of the issues and costs of doing so are major. So there's a rapid development in many contexts towards asking, is there some other material that can be produced either directly or from hydrogen itself that is much more easily and traditionally transported? And the answer, there are several answers, but one of the answers that immediately comes up is, in fact, ammonia. So ammonia is traditionally produced by this Haber-Bosch process from that 100-year-old bit of chemical engineering. In that are some important materials and catalysts. Again, we can come back to that later on. That transforms, if you like, hydrogen, in our case, in the present discussion, green hydrogen, into ammonia, and then of course that is very easy or very readily transported in bulk carriers and pipelines in a relatively standard technology. There is, going back to the electrolysis interest, so back in the realms then of the electrochemists like us, the process of producing green hydrogen by electrolysis immediately raises the question to the electrochemist is, can you effectively bypass hydrogen and produce ammonia directly by reduction, in this case of dinitrogen, or N2 is the feedstock, N is the carrier, if you like, of the H energy. And that's an important area of research today that we're very much part of, and including some of our recent developments that were mentioned on the previous slide. We've recently spun out a company, Jupiter Ionics, which is supported by some of these other government and major industry partners, as you see on the slide here, all focused on scaling up and bringing to commercial realization our green ammonia by direct electroreduction cells. And then that leads in then finally to this picture of the future, what we call hydro ammonia economy. This is purposely labeled that way in order to not completely, in any sense, exclude the role of hydrogen as this transportable energy. There's going to be a role for hydrogen, of course, and ammonia may be, and certainly will be in the short term, a carrier of hydrogen energy, transforming the ammonia back to hydrogen at point of application. So if green hydrogen is produced in the northwest of Australia, it's shipped as ammonia to Japan, where it is somewhere at port or in the center of Tokyo at the local fill station. It's transformed back into hydrogen to put into your fuel cell car. So that's part of this picture. But the picture then goes further and asks, can we in fact use ammonia, which of course is easily stored? That's an important, those little tanks in the middle of that diagram are important here, easily stored in tanks like that. Can that then become an important fuel in its own right? And then the answer is very much yes. And then if you look around the diagram, you see all of these little cartoons are indicating an application where ammonia itself as a fuel, so no longer necessarily transforming it into hydrogen before it's used, as a fuel in its own right. And and every one of those applications, of course, has its own materials requirements, shall we say, to apply ammonia as a fuel. So with that tantalizing prospect of the hydrogen ammonia economy, I'll leave my comments there for further discussion later. Thank you.
Many thanks, Doug. And finally, if you could close things up for us, E.
Yeah, sure. Thank you. I'll wait until Doug can share the screen.
Yeah, I'm struggling to do that. Oh, stop share. There it is. Sorry. Yeah, there we go.
Okay. Hi, everybody. This is E. I'm a faculty member at Stanford Material Science. I want to do a 5-minute sharing about, in a bigger picture, what's happening at Stanford. This is connected back to the materials, sustainable materials. Since the last year, I took over the director position for Preco Institute for Energy. So our institute is managing all the energy activity at Stanford across the whole campus. The vision is sustainable, affordable, secure energy for all. All the keywords important, remember right here. And during the time of Russia, Ukraine war, secure stands out a lot. We have to remember that. We all know what's going on in the whole world. The country committed to the climate goal, company committed to climate goal. Let me share with you, very exciting. Stanford is starting a new school, this bottom bullet point right here, on climate and sustainability. There will be about 10 new departments to be set up. In the statistics, they will have 150 to 200 faculty in this whole new school. Stanford has not started a new school for 70 years. This is first time in 70 years. This is a big deal. Louis, let you know you care about sustainability. Everybody here care about sustainability. This is the scale Stanford is putting behind to address the sustainability issue. So at Stanford, we have nearly 300 faculties, more than 1,000 PhD students and postdocs working on energy, right? Ranging from science, engineering, to technology, to policy and economics. And we have accumulated over the past 20 years since our global climate energy project time, really top talent, a large number to address the energy challenges right here. So Institute is cross-cutting the whole university, including all the schools. The reason to set up an institute at Stanford is really to bring all the expertise together to solve a very, very big challenge. You cannot rely on one school, one department to solve the challenge. You need to bring all the assets together. That's how Stanford would like to do it. It's really cross-cutting the whole university institute. With the new school coming up, we have 4 divisions under the new schools, 10 new departments roughly, and there will be energy science engineering department right there. Preco Institute will be cross-cutting the whole university as a founding pillar of the new department. Let me highlight sustainability accelerator right here. This is a big deal. Stanford, I don't overclaim the credit. In reality, Stanford spin out Silicon Valley. And with the sustainability accelerator right here, you can consider Silicon Valley is turning into a sustainability valley in the coming few decades. So we are going to, do the translation of technology and policy solution on sustainability. So how do we organize our act together to decarbonize the economy? really look into where's carbon coming from: electricity, transportation industry, residential, commercial, and agriculture. So at Stanford, we are all organizing our act together by having multiple initiatives between what to decarbonize electrical grid, integrate solar and wind, and grid-scale energy storage. A few years ago, we launched Storage X initiative, basically battery existing insight. I helped launching this initiative as a faculty co-directors. Natural gas initiative, how do you utilize natural gas without emitting CO2? Catalyst Center funded by Department of Energy, and the Material Center funded by Department of Energy as well. As we're speaking, we are going to launch carbon removal initiative, hydrogen initiative, and sustainable manufacturing, including steel, cement, plastics, and digitizing the whole economy, digitizing the whole manufacturing, as well as related to today's topic of circular economy, right? Having the material sustainability. Also very important, how do we do sustainable finance, policy, education, external communication? This all cross-cutting using data and AI to plan for the future energy system. Super important. Technology translation, social and human behavior, environmental justice, global engagement. I mean, this is a whole ecosystem at Stanford right here, how we tackle energy problem and the climate problem. So, I mean, speaking now for my own lab, over the past 17 years, after joining faculty, is really focused on materials for sustainability by inventing new type of technology for high energy density batteries. I spin out amperes using, this is silicon nanowire technology. And how do you do the air filtration to remove particle pollutant? New type of nanofiber technology we invented. I co-invented with Professor Steve Chu. We co-founded 4C Air. Turned out to be during COVID-19. We have the highest energy facial mask with the best breathability in the world and the KN95 and 95 level. I also set our technology accelerator, licensing more than 20 patents from Stanford to spin out in the venue, grid-scale energy storage, live lab, new type of cooling and warming textile, turn into clothing. Right now, online on sale, you try out. We have the best warming textile, best cooling textile ever invented by human being. Water filtration, soil cleanup, and green building materials. Each of these topics depends on materials. I want everybody to change the unit you measure the material you need to use. We are talking about gigaton scale. Removing gigaton scale CO2, you have gigaton scale of batteries, you probably need to use a 0.1 gigaton scale of filtration materials. You need to have gigaton scale, grid scale energy storage, really gigaton scale of clothing. So everything is so big. Materials for sustainability, circular economy, and finding the resources, utilize, recycle the resources will become very important. I will stop right here. Happy to participate in the panel discussion.
Fantastic. Thank you for that, E. The very inspiring approach at Stanford, bringing together, weaving together all of these different disciplines. I think that's definitely something. It's very true. We need a cross-disciplinary and interdisciplinary approach to try and resolve many of these issues. So in the interest of time, let's jump in, ask some questions. What I suggest is if anybody wants to jump in on somebody else's response, raise your hand using the icon and I'll come to you. And hopefully we can have a bit of interaction. Maybe starting with you, Elsa. So you mentioned a great deal of challenges in your presentation, and one of the points that you touched upon a few times was this rising environmental and social concern regarding the impacts of mineral developments. And this is one of those important aspects of the supply chain risk equation. I'm just wondering, from your perspective, to what extent is this considered as a limiting factor right now? Is it often hard to quantify impact, particularly in terms of financial impact. Is it equally weighted compared to some of the other constraints, or are we still seeing development in this area?
So just to be sure, I understand the question. Thanks for the question. It's just the kind of degree to which environmental considerations are playing a factor now. Am I understanding the question correctly? Exactly.
Yeah. So if we are they being fully integrated and concerned to their real cost, their broader cost? If they are, great. If not, is this going to place even further constraints on material supply?
Sure. Yeah. So certainly not all the externalities are taken into account as we know too well, and that is a kind of a point that I kind of hinted at when I was talking about the overall environmental impact, that we'll start to see increased, pressures on the material supply chains, in part because of the share of energy cost in total mining cash costs and electricity intensity. So there's a whole myriad ways we could think about that in terms of carbon tax, or in terms of factoring in, the obvious significant environmental impact locally. But, something like copper is 20% of the energy cost is in total mining cash cost, and the electricity cost in refining and smelting for copper is 25%. So though, and I'm speaking in very kind of blunt financial terms, if we do better jobs incorporating the externalities in there, that'll drive those prices up, just because of the percent of that. So I think the ways in which I talked about kind of the floor associated with materials cost as a function of downstream manufacturing processing, would be even further exacerbated by that. There was another point that I was going to make there, but yeah, so definitely is not, I know. So that's one juxtaposition of just sort of, as we have those increased social pressures, that'll drive, further volatility, further things we need to incorporate. And then a little bit to the point that Alissa was making, I mean, right now, the kind of, if you think about the sort of supply chain costs associated with primary versus secondary materials refining, they're very different in terms of what's taken into account, and the kind of permitting and social cost of ownership, et cetera, are not apples to apples. So that's another kind of reconciliation. We've heard that from some of the electronics companies we work with, is that the costs associated with using secondary materials are quite high because of the degrees in which the externalities are not come to bear in primary extraction, right? So having those be kind of more cost competitive, I think, to some extent could drive further circularity in ways that would be quite positive. So hopefully that's helpful.
No, that's really interesting. And I wonder, Alissa, you work, I believe, with life cycle assessment quite a lot. Is it challenging to factor in the kind of social, human rights externalities into that kind of analysis? Are there ways that we can account for that better in our consideration of the full value chain of these materials?
Well, I think there are two challenges for life cycle assessment. One, and it was great to hear Damien talk about some of the efforts happening in Australia there, but one of them is that if we can do life cycle assessment on let's say that we have all the data that we need, we can do a good job. And the let's say is a lot of hand waving, because sometimes we don't have data from the actual industry members who are doing the actual production. But if we had all that data, life cycle assessment is really about environmental impacts. And it looks across the supply chain, and it often ignores where things are happening. It doesn't have to, but it does, because these supply chains are really complicated. I might have data for one site, one factory, one mine, but all the things coming into that mine or that site, I may or may not have very specific geographic information about where they're happening. So translating those environmental impacts into the human costs is actually harder than it might seem. And I think a lot of people talk about the cost of carbon. Those numbers are very uncertain, but at least they're global. These, and there has to be site specific, it's hard. So I think what we're going to see more of maybe is what a lot of other kinds of, product stewardship type, labels and mechanisms have pursued for other kinds of products, which have to do with very specific conditions of production, whether it's about fair trade, or organic, has nothing to do with metals, of course, but those are about how something is produced and or purchased or exchanged. And those kinds of labels might be more reasonable instead of life cycle assessment, which this is what I do for a living. I think it's so important, but I don't think it's probably the right tool for that, for actually measuring human cost. We need to look differently at that. I will say that one thing that we're trying to pursue is a participatory LCA. So as we look at minerals extraction in California, the community guides tell us what are the important impacts, what need to be prioritized. By communicating with them, they also get informed in a lot of detail about the production system. And that is part of what we try to do with procedural justice, making sure that affected communities have a say in how the energy system is affecting them. So that's my my run around to your answer, which I kind of didn't really answer your question, but I don't think LCA is the right tool necessarily for that kind of analysis.
No, I think it's a really important point and highlights probably a lot of the big data gaps that we have. And one of the points you brought up there was, this more participatory approach where we involve local communities, the end user, those directly affected in some of these decisions. And I wonder, maybe that brings us quite nicely onto what you were talking about, Damien, in terms of building trust and generating these provenance metrics to indicate where the materials are coming from. But have you managed to overcome some of these data issues that Alissa referred to? Can you do that by focusing on these more specific projects, particularly within, I know Australia is very large, but within a geographical confined space?
Thank you. I think it's certainly a work in progress, and it's important. And I'm really pleased to hear about the work Alissa's got going in California, and that participatory approach to involving communities is so important as we seek to accelerate the pace at which we are doing this mining. And certainly the work in the project that I mentioned as part of this Future Battery Industries Cooperative Research Centre, for its trusted supply chain focus, puts more emphasis on conveying the information, if it's the provenance or the environmental footprint, established through life cycle assessment along the supply chain. For example, in support of, could be environmental product declarations or sort of labels that can make it to the consumer. So there's knowledge about where it's come from. And I think the beginning headline for these stories is often carbon, and we need to also think, as it was good to hear Elsa speak about, the water and the other impacts. And for me, it's important to think, well, who also in this future world gets to what extent are the benefits shared locally or more captured at other parts of the supply chain. For me, it is this transition we will have to do in a way that we all hold together. And I think prompts perhaps also consideration of new business models. Colleagues have been very active in the looking at wind farms and community energy ownership models for these. We don't see that so much yet in the mining story, but if particularly in mining, if there's increasing automation locally, so perhaps fewer jobs, but still some pollution, we need a bit of freshness in the discussion about how those local and other benefits are shared, whether it's the mining, processing, or the operation of some of these new energy technologies to build that trust. Yeah.
Doug, did you want to jump in?
Thanks, Lewis. Yeah, I might be about to bring up something that you were thinking to bring up later on, but we can get into it now. In the chemical energy stores or chemical fuels area, of course, there are devices involved, the electrolyzers and all of the balance of plant, of course, and everything that everybody's just been talking about, of course, applies to those devices. There are various precious materials and et cetera, et cetera. But perhaps somewhat uniquely, there in this chemical fuels area, there's also the life cycle assessment of the material of the chemical itself. Right. If we start with hydrogen, that one may sound dead easy. In other words, we take water, we make hydrogen and oxygen, we later combine hydrogen and oxygen or hydrogen and air and make water again. So the chemical cycle that participates in sounds pretty trivial. And although I wouldn't want to make it completely trivial, I mean, for example, if there are contaminants in water, there could be other products of oxidation other than just oxygen and so on. So there's maybe a more detailed chemical life cycle needed. Circularity needs to be considered there. So that one is not so prominent, shall we say. But when we talk about ammonia, there the question is a very big one. And so I just wanted to sort of point out just how sort of similarly significant this was in the global sense. So now what I'm talking about is actually sort of well known, but not maybe as much known about it as we should know. I'm talking about the global nitrogen cycle, which in talking about using vast quantities of ammonia, making and using vast quantities of ammonia, we're starting to have a significant impact on. That's clear. So the parallel here is, you might say that humankind has spent the last 250 odd years messing up, especially recently, messing up the global carbon cycle. Well, we're now talking about shifting our attention from carbon, solving the carbon problem by shifting our attention to nitrogen, and maybe messing that up if we're not careful. So this is the eyes wide open point that we must observe here. So understanding the circularity of the process that we're about to utilize, and to drill down to, I mean, there's significant sort of complexity here, and in the paper in Joule that we wrote in that I had the reference up a moment ago, called The Roadmap to the Ammonia Economy, we did highlight this and reference some of the field, if you like. It's not my field, but there's a significant field that focuses on this, which is suddenly getting a lot of attention because of the growing attention on ammonia as a fuel. But to finish off this long comment, the point there is, of course, when you transform ammonia in any way, including in an energy developing sense, using it as a fuel, in other words, one of the obvious byproducts that we have to worry about are the NOxes, especially N2O. N2O being a potent greenhouse gas. So we might solve one greenhouse problem and create another one if we're not careful. So understanding the chemical circularity, and that's why my picture, by the way, that I showed here had that nitrogen cycle shown as that circular process, using nitrogen and dinitrogen N2 at point of origin and regenerating only that at point of use. Very important. But understanding the other byproducts and how they may circulate in the environment is a key point here that needs further attention.
Thanks, Doug. Maybe just following up on that, and maybe you have something to add to this. This more systems approach. I mean, obviously, both of you work at the more fundamental kind of lab top level, or maybe at least started out that way. And this kind of broader consideration of the bigger systems aspect, is that something new, relatively new within your fields, or has it always been there? And is it taken to heart, particularly when it comes to new technology design? Are you thinking about the scalability, the potential recyclability, the externalities when you start with a new product, or is there more pressure on performance? I think you mentioned energy density, safety is obviously a big issue for batteries. Is it performance first? Is it sustainability first? Is there a transition happening between the two?
Yeah, Louis is excellent questions. I would say it's a balance right there. at Stanford right now, there's multiple people really putting the thought of, like Steve Chu and Alu Majanda. These are the previous DOE, leadership position. Is thinking about system level analysis first, to having a system view. Well, when you turn the knob, you got to have an effect. If you only look at the component level, you might pick the wrong problem to solve. That's number one. Number two is you don't have the scaling in mind. Then you might go through a detour process, very long detour, before you get the right answer. So having the system level view in the mind, in your mind, and yet at the same time balancing, individual detail idea of creativity. I think that's something we really want to encourage. I, as a director of Critical Institute, I want to encourage people to think so. If they go into very focus of performance level and that device, then I will challenge them. I said, what about the scale? Have you thought about that? Put that into the mind also. Of course, if you're the only thing about scale, there's no creativity, performance enhancement or cost reduction. That will not work either. That needs to be a balance. Yeah.
Yeah, I mean, I see a lot of some of the new technologies coming out, particularly in the battery space, looking at using more earth abundant elements rather than the more critical elements. And it seems that one of the key sticking points is always commercial.
Absolutely, Louis. I think so. That's very important right now. You find out, well, you get lithium cobalt oxide to work. Cobalt is limited, right? And Elsa's talk very clear. And nickel will start to show up. And then lithium, maybe not as much, but also start to showing certain trend. Then you say, well, if I can do sulfur, like lithium sulfur battery, sulfur is fantastic to replace cobalt and nickel. It's abundant, high energy density. Although, of course, it's very hard chemistry, very hard to make it to work, but it's worthwhile to work on it for the next generation.
Yeah, and Elsa, correct me if I'm wrong, but I think that some of the IEA scenarios that you're referring to in your talk, some of that uncertainty comes from climate pledges and our government's going to deliver. But then I think a big chunk of that uncertainty comes from that technology, that particularly future battery chemistry. Do you see, are we able to kind of bend some of these material demand curves through a technology transition, or in your experience, it just take too long? I mean, if we combine, the technology, the scalability, the sourcing of new minerals, as you mentioned, over a decade or almost 20 years for a mine to go from discovery to prospecting to actual activity. Technology comes up as a solution quite often. Is it feasible in this with this challenge in mind, at the scale, at the rate needed?
Yeah, no, it's a good question, and it's the devil's in the details, right? Because some of the transitions that are being talked about, in some cases are improvements on chemistries that we have some scaling experience with, right? And, can be more drop-in, like a lithium iron phosphate, where we've had performance improvements, and we're being more thoughtful about best application of best technology, right? And so then it's the really critical scaling and temporal challenges that have been talked about throughout are, have a different sort of a lens on them. So I think, my point was it's difficult to bend the trajectory for new technologies like solid state batteries, for example, over the time horizon that things need to reach scale. It's nigh impossible. But there's a lot there that has to be thought about. And you mentioned the Climate Sustainability Consortium that I co-directed at the beginning, and there we've had the pleasure of working with several companies, really where their questions are around their own technology investment, not in the sort of specifics of particular battery, but how do they think about the trucks, the over the road trucks they need to think about to, the right supply demand for just the what makes them interoperable, what makes them chargeable, right? So the multitude of issues in each of the aspects of the value chain mean that new technology is really difficult to kind of have the same impact on the time horizon that we need to. One thing we've tried to do a little bit to your materials question is think about what are the characteristics of a material supply chain that make it more robust to the kinds of sharp increases in demand or challenges in recyclability and elasticity, and can we have a bit more general frameworks to try to evaluate these things, to try to develop mitigation strategies. And so I think that's been kind of a theme that's come out throughout the discussion today. So it's a challenge for sure in the new technology way. I mean, new technologies to display. So thinking about these things in terms of, what's going to be drop-in relevant now, and then how do we be running the right pilot experiments in the 2020s to be ready for what's happening in 2030, right? So I think trying to be a little bit more forward-looking than we are famous for as a species.
Yeah, absolutely. So doing better with what we have rather than maybe trying to invent the wheel given the time horizons that we're working with.
Yeah, or at least acknowledging when that wheel is going to have impact, right? And so that, I think it's still important to be investing in the basic sciences and the new wheels for sure, but let's, it's kind of right place, right time sort of thing. And what is it that we need to be thinking about for the technologies in 20 years relative to thinking about those as solutions for now?
Absolutely. I'm muted. Going back to you, Elissa, you mentioned in your talk this more experimental approach to mining lithium in California and taking this kind of more, holistic and participatory approach. Kind of factors into this doing better with our current approaches and what we have now. Is that how you see this, or is this more of a smaller abstract project?
Well, here in California, we like to think that we do things first and people copy us. So hopefully what we do here will actually catch on elsewhere. But I want to say yes in some ways, but also maybe build a bit on what Elsa said about planning for the future. So the first part of my answer is California is trying to do this a little bit differently by including community members and industry and agencies all together. My group's doing the participatory part, and we're not part of the government, but we hope we have their ear, of course. But I do want to talk a little bit about maybe the broader role of governments and policies on also doing this. We can talk about the economics, but and sort of R&D work, but there's like a push and a pull, right? And giving industry some confidence in what the future will be can maybe facilitate investment in commercializing technologies and maybe have a little bit of a pull on things. But it also changes the math on what's going to be not just feasible, but profitable in a lot of ways. And I just want to set the stage. We could look at the EU and its new proposed battery regulation. China's at least focus in the past on circular economy and some of the investments there on recycling, and then the US, and contrast what that means for these technologies. And I'm just talking about like battery recycling. So for example, the EU has proposed recycled content standards, very, very polemic to say the least, but those standards are a real pull, right? For recycling technologies to develop and for industrial development as well within the EU, because it's kind of a coherent policy with respect to trying to internalize the supply chain within the EU. China's already done some work there, and each of these regions have very different sort of governmental structures, of course, as well. But in the US, we have none of that coherence. We don't have any national policy on what to do with end-of-life batteries, for example, other than how we can transport them. But we don't have a rule that they have to be recycled. We don't have any of that in place. And so there is a very important role for government to play in basically shaping what the future will hold and giving confidence to industry or essentially to commercialize technologies differently. And I think that that's kind of an important parallel to think about is that it's not just about sort of pure economics, but the policies that different regions and countries might put in place.
Yeah, I think that's a really good aspect to consider. And I mean, my understanding, and please someone correct me if I'm wrong, is that the investment, or maybe better to phrase this as a question, is the investment that we have at the moment, that we're seeing at the moment within low carbon technologies, is it what we need, or how far away is it from what we need? My understanding is that the deployment of renewables in particular is rapidly occurring, but it's only just keeping pace with increased energy demand. If we wanted to cut into actual fossil fuel capacity, then much more deployment is going to be needed. Are we seeing the levels of necessary investment? Maybe Damien, have you got anything to comment on here, given that some of your interactions with the different groups that you're working with?
I think you make a good point that whilst scale's going up, the required scale is also very steep. The one point, hopeful point, I think I've observed in recent years has just been the focus not only of government, the private sector coming, and the money that is looking to be invested in areas like the renewable energies we are talking about. But it's not to underestimate the sort of whole scale change of rewiring countries and energy systems, and going from many cases from centralized to decentralized, or managing the integration of electric vehicles into the grid and so on. So there is lots and more that needs to be done. And I think it's important that where we feel we're heading in the right direction with a technology or a focus or approach, then yes, let's focus on deployment and removing barriers to scale. Where it's really unclear what might be a good way to go in an area, or how, for example, Doug was talking about, to get ammonia more used directly as a fuel, then how can we bring science to trialing, learning, thinking about scaling, and just being proficient with pursuing multiple strands at once with a few learning loops that still keeps the bigger picture in mind of where we need to head. I think it's tough, but it's important.
Yeah, I mean, it seems that we need to, if we can resolve some of this uncertainty, and this big uncertainty regarding what world are we heading towards? Are we heading towards net zero? Are governments on board with that? If we can nail down that certainty, perhaps there's a next step then in terms of industry and investment and commercialization. But it seems at the moment the level of investment is maybe more aligned with a gradual energy transition rather than the rapid energy transition that we actually need. And I'm just wondering, maybe again, you, Damien, in your experience, again, from my understanding, the energy sector is actually a relatively new user of materials at this scale. Or at least it's ramped up significantly because of the low carbon transition. And I'm wondering, and anyone feel free to chip in, I'm wondering, does that kind of newness that you have with organizations using materials, that make it easier to kind of govern the different supplies and flows and standards and expectations? Or does it make it harder because perhaps competitiveness and profit is still quite new and quite a high priority for these different stakeholders?
It's an interesting question. I think getting the niches established, does offer some collaboration, and some of the collaborative arrangements we're part of with industry and supported from government and universities are really, I think, critical to helping bring some of the new technologies to a more advanced stage. But you can imagine when it gets to fundamentally disrupting the incumbents, who it can be tricky, and we need to think about the coalitions to form to progress that. I think energy too is it's got a lot going for it, and we can see how to get there. I think there are also, perhaps it goes beyond some of the focus for this panel discussion, but all those harder to decarbonize sectors also should be, in the back of our minds. And it, for me, making it just brings in a little bit thinking about efficiency and value, not necessarily within the same view. I think it's taking more of this systems view, and where there are new values to be shared in the supply chain, for example, from using the responsible sourcing of lithium mined in Australia with credentials that are strong for social and environment, and goes into a electric vehicle, that the consumer can have confidence about the supply chain. How do we share those financial and other benefits in new ways that can help us accelerate deployment? Yes.
Yeah, I'm the point you just brought up then. Sorry. You carry on.
Yeah. So I'm trying to say is, for example, recycling battery technology is not something like completely new. Lead acid battery has been doing that for so many years, right? With recycling rate 90-something%. And lead acid market is as big as lithium ion. It's similar, right? The global battery market this year is $120 billion market. Lead acid and the lithium ion are similar. So people figure out how to do lead acid, but to be fair, lead acid is a lot easier to be recycled. The anode is lead, the cathode is lead, right? Lead dioxide and lead. It's the lead grid. That's why it's designed. It's designed right that the chemistry determines it's easier to recycle. Also, it's easier to collect as well. You don't see a tiny cell lead acid battery, at least like a car size batteries right there. So it's a lot easier. Lithium ion is facing this challenge with tiny foam batteries all the way to the whole battery pack for the transportation. And the lithium is so hard to recycle. The cost is much higher. You take out lithium, take out copper, cobalt, nickel. You all need to separate it. I mean, that's much harder. So I will challenge the research field and say, well, down the road, let's design the battery a lot easier to be recycled to start with. Keep that in mind. I don't know what it is yet, but it's an R&D direction.
I think it's a really interesting point. And I mean, maybe a connected point is, again, my understanding is that for lithium-ion battery recycling, it requires a lot of toxic chemicals, quite harmful substances. So is that another consideration? It's not only necessary to have a battery that can be recycled, it's necessary to have a battery that can be recycled safely without having these additional...
Absolutely. There's so many components to be separated. You go through so many processes, strong acid, for example, and still doesn't work well yet. You need to have multiple type of chemicals coming in.
And maybe Doug, sorry, Alissa, I can see your hand there. Feel free to jump in.
Oh, I just, I wanted to echo a bit of what you said, but also add to it and say that, lead acid batteries are a great story about recycling, but they're also a terrible story about environmental injustice. And this is because of recycling sites here in the US, for example, in California, where people perceive us to have really strong environmental laws. We have communities that have decades of lead poisoning because of because of lead acid battery recycling. And of course, in lower and middle income countries, we see very poor conditions for lead acid batteries. So I think we should take the idea of designing batteries to be recyclable, but also make sure that we don't replicate what we've done in the past, and make sure that there are protections for the communities and people affected. And this is a little bit off topic, but I just want to put it out there that, we already have a very robust electronic waste trade in the world. And that trade might include a whole lot of clean energy technologies, whether they be batteries or photovoltaics in the future. And it's something that we should be thinking about. And it's important to think about for circularity as well. And where these things are going and whether or not it's really feasible for them to be recycled where they're going. And as he pointed out, it's much harder to recycle a lithium-ion battery. So I'll stop there.
No, I think that's a really important point, particularly with acid-lead batteries. Doug, I was just going to ask something similar. Within your group, you mentioned earlier on, I think, we don't want to come up with the solution and cause another problem. It's important to think about this more circular nature. And within your group, what do you see as your kind of, focus projects at the moment to identify some of those new solutions without contributing to other problems?
So from our point of view, it's I think we've kind of focused on two different aspects of this. One is kind of what I did before, which is as humble electrochemists who know relatively little about the huge environmental cycles that I'm actually talking about here. It's just simply always making as much noise as we can to raise awareness of this big issue, which it falls into the lap of atmospheric scientists, of marine scientists, of freshwater people, et cetera, et cetera. So this is a huge community, shall we say, where I think more needs to be done and understood. So that's kind of one role. But at a more research bench level, we're very much aware of the need to track down every last nitrogen atom or molecule, right? So that we are aware of, we can't just be satisfied with 99% Faraday efficiency. We need to know what the remaining 1% is. In case that, once you multiply that by 10 to the 9 or 10 to the 12, could be a significant environmentally damaging byproduct. So keeping a strong focus on understanding the entire picture, balancing the chemical books entirely within our means, so to speak, is part of the attitude towards that. And as an example, we're working on a process at the moment for the oxidation of ammonia into more useful materials as fertilizers. And what we don't want to do is produce any more N2O, nitrous oxide. That's the one that I mentioned before is a very, very potent greenhouse gas, than is currently the case in traditional chemical engineering processes. So it is this is already part of the fertilizer story is that it does the production of fertilizers produces nitrous oxide. Our goal is to constantly be monitoring what our process is producing, and it's clearly got to do better, but we would like it to do a lot better than the current process.
Absolutely. I'm very aware of time. I want to just come back to you, Elsa, before I maybe give each of you just a closing remark each. It seems, based on your presentation and everything we've heard here, it's both a very exciting and daunting time, perhaps, to work in the kind of material science space, whether it's at the fundamental scale or at the other end of the system scale. Do you see future research as being collaborations among different elements of material science, or are there other disciplines that you feel are key? So what would you say are the key kind of cross-disciplinary collaborations that are needed to really advance some of these solutions?
Thanks, Lewis. You a little bit read my mind. There was a slide I didn't have time for at the end that I kind of asserted this at the very beginning. I really do think that we have to get really good at cross-cutting, deep collaboration, and it's really hard across political scientists, across technology, science, and engineers, across social scientists, energy, economics, analysis. All those pieces have to come together, and we have to start those conversations in ways where we are learning each other's language while we are solving climate crises, right? And kind of just, I always felt like I worked in an interdisciplinary way because I work across length scales and materials, but I've had that just so proven to me wrong in the work in the consortium, where I've had to do deep work across boundaries, and it's not easy. And I, didn't understand the depth of the challenge there. From on the research side, it's developing really significant research questions on both sides, right, of the academy, and then you also need to be bringing in industry business leaders. So lots of conversations, lots of listening. We need to get a lot better at listening. So I could go on in terms of the level of technical challenges I think we need to solve and how those need to be linked, but I think really taking thoughtful time to learn to communicate with each other is what is really the right starting point, building trust across these disciplines.
And would you say that's your kind of, if we start going around now for everyone to have one final thought before we wrap things up, is that your kind of, in a nutshell, what you feel needs to happen, or is there anything bigger and broader that you feel is the key priority to advance solutions?
Yeah, I think so. Solving across length scales, solving across disciplines, and being comfortable with nuance, I think, and learning how to communicate nuance to the general public and each of us as consumers of information, is going to be critical for us to be able to get out from under ourselves.
Yeah, one size rarely fits all, I think, in this world of grand challenges. Alissa, do you have a final remark you'd like to leave the audience with?
Well, I'll echo everything Elsa said. I don't think I can say it better. But I actually have, I have two things that are almost in conflict with one another. The first is that I think it's really easy to talk about the harms and barriers of the decarbonization strategies that we're going after. And we rarely couple it with reminding everyone about the harms and damage that our fossil energy system and our carbon intensive production systems have done for the past 200 years, 100 years in particular. And so I have worked in a lot of public facing environments where regular people will say, well, electric vehicles are terrible for the world. I heard this radio, I read this story about how bad batteries are and that they're worse than gasoline. And we need to be sure we don't focus so much on the negatives of these transitions that we sort of, lose sight of what we're trying to solve. So there's one side of the coin, and then the other is kind of echoing Elsa's point. I think one thing that has come through in so many of the big conversations that are out there is the need for us to be much more active in thinking about a just transition. And thinking about, all the peoples who are affected by the energy system, whether it's on the access side or the impacts of production side. And so I think we can do it better this time around. We have an opportunity because we're building right now to do it right. And that's where I hope we spend a lot of time focusing our attention and investments.
A really important point. Thank you. Damien.
Thank you. They're great points. And I think the importance of collaboration across discipline, transdisciplinary research collaboration that we do put emphasis on at UTS, at our institute, I think is really important. And just to build on Alissa's point, it reminds me of a quotation our director, Stuart White, is often reminding us just that we do talk about the challenges and the problems, but good solutions can take off in a non-linear way when we put our mind to it as well. And that's, I think it's really important we work towards that and are also thinking too with this systems view over the horizon, also to solutions that have a different relationship to being dependent on increasing economic growth under its current form, and that we do think of ways of organising society that are consistent with living within planetary boundaries. Just a few specific points that pick up on our discussion that I think are interesting interfaces for future research. One around understanding the resources that we spoke on earlier in today's discussion, and okay, to what extent are the externalities built in? We have really well codified rules for resources where they're economically demonstrated. We know that developing them will be able to make money, but I think we need a bit more nuance to build in the social and environmental factors. So as we're going from those sort of cheap, easily accessible resources to those that can be more complex and expensive, giving signals to the market and investors about that complexity is, I think it's an interesting area. Another one that was sparked, and it's so fantastic to see all the translation happening at Stanford, and thinking how we put our academic knowledge into practice more. I'm reminded also of some colleagues at the University of Queensland who come up with a concept of social license, which we often speak about at the mine site, but in design, so that as we're thinking through new technologies, and yes, they could be great, as we look forward to deploying them at scale, are they also likely to be well appreciated by the community? How can we build them into that story? And just a last one on the circular economy, as we're talking about, recycling lead acid. It's good for the systems because, in part, it's a simple design, notwithstanding the effects we'd seek to avoid for communities where some of that takes place. But for me, it's also got an inherent material value that underpins the baseline of the economics of the recycling. And I know some of the lithium batteries recycling, even the cobalt in there was helping to underpin the economics of that recycling. So as we move away from that, to what extent do we seek to rely on inherent material value to underpin the economics, or other stewardship models and levies like battery stewardship that we're working to implement in Australia now to bring about that circularity that we would hope for?
Thank you. E, your final thoughts?
I'll be very quick in the spirit of final thought. I want the audience to remember this is a scaling problem. The reason we talk about circular economy is really for scaling as well. Change our unit of thinking. In the lab, we work on milligram of materials. We are now talking about gigatons. We are talking about 15 to 20 orders of magnitude difference right here. So we need to remove in the order of 40 gigaton of CO2 or more. The battery size we are talking about for a billion car, we are talking about also gigaton of batteries right there around that neighborhood. And many technology, we are using giga as the unit, remember that. So that should going into our research very early in thinking. The scaling is important. Finding the mineral resource is important. Circular economy is important. And I'll just stop right here.
Thank you. And finally, Doug.
Thanks, Lewis. Lots of good things being said already here, which I completely concur with. If I could add one thing, it probably comes from a question that we've written in the Q&A box, and I've just written a typed answer to that. But in summary, it related to it raised a really interesting point that I think is what is needed, or we need a lot more of this comparative analysis. The question related to what's better. I'll paraphrase the question. What's better, a Tesla or a Toyota Mirai? Battery electric versus hydrogen fuel cell, and in terms of materials. And the answer in terms of the two devices in the two cars is probably going to come down on the size of the side of the fuel cell. But then if you have to add in all of the hydrogen production and transportation and supply infrastructure and those materials needs, but equally on the other side, you need to look at the materials aspects of getting all that extra electricity into the locations where the batteries are going to get charged. Et cetera, et cetera. And my point is that it's the comparative analysis on a genuinely system, if not planetary-wide scale, and fairly done, so to speak, is I think what we need more of. And I don't think we can rely on commercial forces, if you like, to produce the outcome that is the rational outcome that is needed here. I think this is going to have to be probably an academic exercise in getting the methodologies agreed, and then the analysis executed, and that's a task in its own right, because it's a big task, in such a way that we can come up with rational comparisons of different technologies.
Absolutely. I think material sustainability within planetary boundaries is certainly a grand challenge, and it will be interesting to see how it unfolds in the, well, I hope the coming years, because we don't have decades to resolve this challenge, unfortunately. Well, on those remarks, I'd like to thank everybody, bring this panel to a close. Thank you, Elsa, Alissa, Damien, Yi, and Doug. I really enjoyed this conversation. I wish we had more time, but unfortunately, we have to bring things to a close. We'll now, for those watching, we'll now have a nice minute break before the next panel comes on. So in some parts of the world, go and get some lunch. It's 6 a.m. here, so I'll be going to get some breakfast before probably going to bed after the previous sessions. Thank you, everybody, once more, and everyone take care. Goodbye.